Bismillahirrahmanirrahim. We meet again in online class, asynchronous class, to discuss about chapter 1, Introduction to AC Circuit. So today our discussion will be on the third part of the chapter 1, and today we'll cover impedance. So what is impedance? Impedance, written as Z or Z. AC steady-state analysis using phasors allow us to express the relationship between current and voltage using a formula that looks like Ohm's law. V equal to IZ, and Z here is the impedance. Z is called impedance, same units as resistance, ohm. Okay, units ohm, impedance. Impedance is often a complex number, but it is not a phasor. Okay, meaning, what is the meaning? Impedance depends on frequency omega. Impedance often complex number but not a phasor. So normally we write impedance in a complex number, but it is not a phasor. That means we don't convert the impedance into the same that we do for cosine sine wave equation. Okay, phasor relationship for circuit element. Resistor, in the phasor domain, resistor, the impedance is equal to R, resistance. The impedance is equal to resistance in resistor. Voltage current relationship is given by V equal to IR. That means I and R is the same phase. This is the phasor diagram for circuit using a resistor. V and I are in phase. In this figure, it shows that the phase of current is similar to phase of voltage. That is the case for the resistor. Next, inductor. This is a pure inductor. In inductor circuit, the phasor domain is equal to Z equal to J omega L. Voltage current relationship is given by V equal to J omega L I. So J omega L multiplied by I. So this is the phasor diagram for relationship between current and voltage in the circuit having pure inductor. So we can see that the phase angle of voltage and current is at 90-degree difference. So in this case, we can say that VL, or the voltage, leads the current I by 90 degree. Hopefully we still remember about the leading and lagging of the signal, of the sinusoid signal. So in this case, we can see that VL leads IL by 90 degree. This is for inductor. Next, we have the capacitor. The phasor relationship for circuit element in capacitor. In the phasor domain, the impedance of the capacitor is equal to minus J over omega C. So voltage current relationship is given by V equal to minus J over omega C multiplied by I. So in this kind of circuit, we can have Phasor diagram like shown in the figure, where we can see the I, the phase of current and phase of voltage is different at 90 degree also, but in this case, this time VC or the current the voltage lags the current by 90 degree, or we can say that the current leads the voltage by 90 degree. It is different from the previous, totally different. So this time VC voltage lags the current by 90 degree. So if we have the circuit, we have all those elements RLC, we can write the general expression for the impedance Z as shown here. So Z equal to R plus minus J X in the unit of ohm. This equation is the general expression for impedance, where R is the resistance element and X is the reactance element, which depends on the value of capacitance or inductance. So Z is equal to R plus minus J X in the units of ohm. This is, if we can see here, this is the rectangular form of complex number. So this is the summary of impedance. The resistor Z is equal to R, and the phase angle is 0. So the reactance is 0. Inductance ZL equal to J omega L. So J omega L with the angle 90 degree. So the reactance XL equal to omega L. For the capacitor circuit, ZC equal to minus J over omega C, or we can write 1 over omega C with the angle of minus 90 degree, and this we can say that XC equal to minus 1 over omega C, the reactance. Impedance and admittance of passive element. The admittance Y is the reciprocal or 1 over of the impedance measured in Siemens. So Y is 1 over Z. So this summarizes the value of impedance and admittance. So for R, Z equal to R, so Y is equal to 1 over R. L, Z equal to J omega L, Y equal to 1 over J omega L. The reciprocal, so C, Z equal to 1 over J omega C, Y is vice versa, or J omega C. That is, what is that? That is the admittance, the reciprocal of impedance. Example. Okay. The current in the 75 millihenry inductor is 4. This is the current 4 cosine 40 kt minus 38 degree milliampere. Calculate inductance, the inductive reactance. This is the X, the impedance of the inductor, the Z, phasor of voltage. This is the phasor, the voltage, and the steady state expression. This is the equation Vt, the cosine cosine equation. Example 5, find the Phasor domain equivalent circuit for the following circuit. So you can add this 50 plus J plus this admittance, sorry, this capacitance and this inductance. Convert this into Phasor. Next, series impedance. So series, because Z is equivalent to resistance, so we can simplify this equation as we handle resistance. So Z equivalent is, for the series, is Z1 plus Z2 plus Z3. So we can simplify this Z1, Z2, Z3 to become one equivalent impedance, ZEQ. Same wise, if we have this parallel impedance Z1, Z2, Z3, we can simplify this three impedance into one equivalent. You can use this equation: 1 over Z equivalent equal to 1 over Z1 plus 1 over Z2 plus 1 over Z3. Or we can say that we can use the admittance equation. Okay, the last, you can try this exercise. Find the input impedance of the circuit. Find the input impedance Z in for this one. Assume that the circuit operates at omega given at 50 radian per second. Omega is 50. So you can try this first. So Z, how you simplify this? So first, calculate for this RN L, this RN L inductor, and then parallel with this RNC, and then plus this one. Okay, this is normal operation of, first convert this into X, the value of X, J omega we discussed just now, and then calculate the value of Z in. So the answer is given already, so you can try write on your own first. So that's all. We will discuss about we will discuss about this exercise in the next class. Okay, that's all. Thank you very much.